in Excel, we can take a base 10 logarithm of a complex number using the IMLOG10 function. The IMLOG10 function is quite straightforward. So I type =IMLOG10, and then I need to supply one number. This number needs to be in a complex form. In the left-hand column, I have some complex numbers. Now do keep in mind that complex numbers are considered strings or text in Excel and not as numbers, so they might not always be that easy to work with. Now in this case, we supply the complex number to the function. Notice that some of the numbers I have in column A contain real parts, imaginary parts of both of them. Now you can recognize the imaginary parts because they have an I next to them. So the current complex number has 2 as a real part and also 2 as an imaginary part. Now I close the parentheses and I pull this down. Now what you can see is the result of a base 10 logarithmic operation on a complex number. Now earlier I mentioned a complex number has both a real and an imaginary part. Well, the abbreviation IM from the IMLOG10 function in Excel stems from this imaginary part. Now as you can see, for every complex number we are getting a result except for the number 0. Now the complex number is represented on a complex plane where the x-axis represents the real part of the number and the y-axis represents the imaginary part of this number. Now to perform further calculations, we will have to split the real and imaginary part from this complex number. Fortunately, there are some functions in Excel that allow us to easily do this. The first one is the IMReal function, which we supply a complex number and it will return to us the real coefficient. So I close the parentheses, press enter, and I will be pulling this through. Just like we did with the real part, we can also extract the imaginary part using the function imaginary. Now, the imaginary part will return the imaginary coefficient of a complex number if we provide it with a complex number. So I close the parentheses and I pull this through. So now you can see how the complex number was created. We have a certain real part and a certain imaginary part, and combined they form a complex number. Now the notation you can see in column A to the left is a rectangle form notation of a complex number. Like I mentioned, it is a coordinate system, and so the x-axis represents the real part. So for example, this number would be 1 to the right. And then we have the imaginary part, which is plotted alongside the y-axis. In this case, the imaginary part is -2, so this coordinate would be 1 minus 2 on the complex plane. Now we can also denote a complex number using a polar form or an exponential form. In this case, we will be making use of the exponential form. When we are working with the exponential form, we are expressing the complex number not as a number of coordinates, we are expressing it as a certain slope we need to take and then take a certain distance from the center along that slope. Now the structure of such an exponential form notation is r times e to the power of theta I, where e is Euler's number being 2.7, 18, 28, etc., etc. And then we need to define r and theta, I of course representing the imaginary part. Now r represents the distance from the center up until the point plotted on our complex plane, whereas theta defines the angle we need to take from the x-axis to reach our destination point. Now r, which is the distance from the center of the complex plane all the way to the complex number plotted on the complex plane, is equal to the square root of x squared plus y squared. Now this formula is derived from the Pythagorean theorem and we use this very frequently whenever we are calculating distances. So let's go about this. We can use the sqrt function, which performs a square root on a number. Now the number on which you want to perform the square root is the real part brought to the power of 2. Remember, the real part of a complex number is plotted on the x-axis. And so then we add to this the imaginary part to the power of 2. And remember, the imaginary part is plotted alongside the y-axis. I close the parentheses and I press enter. And as you can see, this will get us the distance from our point to the center of the complex plane. So now we need to calculate theta. Now theta, which is the angle formed by our x-axis and the line which we will be drawing through the center and our complex number, we can come up with this using the arctangent function. Now in Excel we write a tan 2 which will return the arctangent of a specified x and y coordinate. The result will be in radians. So first we supply an x coordinate, afterwards a y coordinate. So the x coordinate is of course the real part of our complex number, and the y coordinate would be the imaginary part of our complex number. I close the parentheses and we are pulling this down. Now that we've calculated the r and the theta, we can recreate the exponential form of our complex number. Now do remember that complex numbers are represented as strings within Excel, so we will need to do some string concatenation in order to create this exponential form. Now the exponential form starts with the air, being the distance from the center to our complex number. So I will be rounding this down to 2 digits, so I use the round function, and I take the r and round this down to 2 digits. Then I concatenate this using an ampersand operator to e to the power of, and then I need to define theta I. So theta, that would be whatever we calculate in column G, but I will also be rounding this down, so I use the round function to select the variable for theta and round it down to 2 digits. Then I concatenate to this the letter I. I press enter and we pull this through. And so as you can see, we have recreated the exponential form of our complex number. Now the reason why we took the exponential form of our complex number is that we can now more easily perform a logarithmic operation on our number. We will specifically be taking the natural logarithm of our exponential number. And this has a very nice advantage, is that the e to the power of something is cancelled out by the natural logarithm. So this is exactly what you can see here in column J. Now, when we take the natural logarithm of our exponential form, we can apply the logarithmic rules we would also apply when working with real numbers. For example, when we multiply something within the logarithm, we can actually split these parts up and later add them together to recreate the same result. So that's exactly what we will be doing. So first, we are taking the natural logarithm of e to the power of theta I. Now, this is quite easy. All we have to do is write theta I as the natural logarithm, and Euler's number are canceling each other out. So here I will be writing round, and then I will be rounding the theta down to 2 digits and concatenate this with an I. Okay, let's pull this through. Next up, I also need to take the natural logarithm of r. And remember, r represented the distance from the center of our complex plane up until our complex number. Now, for this, we can use the Excel function ln, which will take the natural logarithm of a number. Now, the number of which we want to take the natural logarithm is defined here in column F. This is already a real number, so this should pose no challenge. I close the parentheses and press enter. Now I will be pulling this through. Now, to reconstruct the result of our natural logarithm of this complex number, we will be adding these two parts together. So first, I will be rounding the real result, which we got by taking the natural logarithm of the distance to the complex number, to 2 digits. And then I add to this, and of course I'm using string concatenation as complex numbers are not considered numbers within Excel, to add to this theta I. So let's concatenate those strings, and there we go. This is the result of taking the natural logarithm of a complex number in an exponential form. Now, to prove that this is actually correct, I will be inserting a new column where we will be using the function IMLOG10. And this function within Excel will perform a natural logarithm on a complex number. So all we do is apply a complex number, press enter, and we will be receiving the natural logarithm of that complex number. Now, of course, I've used some rounding, but as you can see, this matches exactly. So it's 1.4 plus 0.79i. Here we have 0.8 minus 0.46i. So whatever we came up is actually matching. So this proves that so far we have been following the correct steps. So this represents IMLOG10. Let's make this column a little bit smaller. Okay, so we've taken the natural logarithm of a complex number, but what we were really trying to do was to take the base 10 logarithm of a complex number. Fortunately, there exist some logarithmic calculation rules which apply to real numbers, but also apply to complex number. Now for this, we can use a calculation rule, which says that if you take a division of two logarithms, which both have the same base, then we can construct from this a new logarithm that has the base of the number we took the logarithm from in the denominator. So this is exactly what is shown here. So base 10 logarithm of a complex number is equal to the natural logarithm of this complex number divided by the natural logarithm of 10. I will be performing this calculation both for the real and the imaginary part of my complex number. Now first we need to take the natural logarithm of the real part of our complex number. Well, we actually already did this. This was here where we take the natural logarithm of r, and now we need to divide this by the natural logarithm of 10. I close the parentheses and pull this down. Now we need to do the same thing for the imaginary part of our complex number. Now earlier here in column K, you can see we took the natural logarithm of e to the power theta I, and what was returned was basically theta I. So what we are looking to take is just theta, because that is the natural logarithm of the imaginary part of our complex number. So I reference theta and I divide this by ln 10. I pull this down, and now we have both calculated the real and imaginary part of our complex number, of which we took the base 10 logarithm. All that's left to do is add these two parts together. So we have the real part, which I will be rounding down to 2 digits. And I add to this the imaginary part. So I concatenate a plus sign and then also round down the imaginary part to 2 digits. And in the end, I add an I to finish things off. Press enter. I'm pulling this down. And there we have the base 10 logarithm of a complex number. Now to verify that this is actually correct, let's insert a column where we will be once again using the IMLOG10 function. So IMLOG10. And so we write equal sign IMLOG10. This will return the base 10 logarithm of a complex number. And the only argument we provide is the complex number in its rectangle form. I close the parentheses, press enter, and I'm pulling this down. Now, because we get a lot of decimal numbers, let me extend the column to verify if we are actually getting the correct number. And you can see here we have 0.45 plus 0.34i, and this matches exactly. For example, here we have 0.35 minus 0.48i. Well, that's exactly what we're getting there. So as you can see, we've been able to reconstruct the IMLOG10 function to see what's going on behind the scenes. So what we're really doing is converting the rectangle form of our complex number to an exponential form, for which we have to calculate the theta angle and the r distance. And from this, then we take the natural logarithm. Then, using some logarithmic calculation rules, we can derive the base 10 logarithm of this complex number. If you found this helpful, consider subscribing to the channel for more videos like these. You can also leave a tip using the PayPal link in the description. Thanks for stopping by. Feel free to watch this recommended video.